I decided to do an example using strong induction because this one not only uses strong induction, but it uses a recursively defined function. And you might say it looks a little bit like the Fibonacci sequence, but different. Okay, we're going to use strong induction in the following. Here's the problem. Given that f of 1, f of 2, and f of 3 are all equal to 1, 3 consecutive terms, the initial terms are 1. And f of n in general, when n is at least 3, actually that would have to be, n would have to be at least 4 in order to go back 3 terms. F of n is equal to f of n minus 1 plus f of n minus 2 plus f of n minus 3, the sum of the previous 3 terms. So if n is 4, we've got these 3 to determine what it is. So we know that the 4th term would be 3. All right, that's the setup. This defines the function. We need to prove that f of n is less than, strictly less than 2 to the n for all natural numbers n. Well, in this case, our base case is actually a bunch of base cases. Our base cases are going to be these 3. So that should just take 1 minute to do. For n equals 1, we need to show that f of 1 is what? That f of 1 is less than 2 to the 1. Well, f of 1 is simply the number 1. I think what I'm going to do, let's see, f of 1 equals 1, and that's less than 2 to the 1. That one holds true. F of 2 is equal to 1, and that's less than 2 squared, simply. And we got one more. F3 is equal to 1, and that's less than 2 to the 3rd. So we proved that the base cases work. Now, though, we need to suppose, I'll pick a different letter here, a different variable. Suppose f of I is less than 2 to the I. It's this statement right here. Suppose that that holds for all values from, let's say, 1, 2, all the way up to k. So suppose it's true for all of the first k natural numbers. And note that k is at least 4. We already proved it for k, we proved f1, f2, and f3. So this list is going to go up to at least 3. And we're just going to prove that it's true for k plus 1. And that'll be the end of the proof. It's a little bit of algebra. So suppose that's true. Let's write out what I want to show. To show that the k plus 1 term holds. To show that f of k plus 1 is less than 2 to the k plus 1. That's what we have to show is true. All right, so f of k plus 1, by definition, I'll say but, f of k plus 1 is equal to the sum of the previous 3 terms by the definition of the function. F of k plus 1 is f of k plus f of k minus 1 plus f of k minus 2. All right, what do we know about f of k? F of k is less than 2 to the k. Plus, f of k minus 1 is less than 2 to the k minus 1. Plus 2 to the k minus 2. Since this number is less than that, and this number is less than that, and this number is less than that, the sum of these 3 numbers is less than the sum of those 3 numbers. And at this point, I could factor out, I think I will, I'm going to factor out a 2 to the k. So this is actually equal to 2 to the k times, starting off with 1, plus 2 to the negative 1, plus 2 to the negative 2. If you're not convinced, just use the distributive property here to make sure when you multiply through by the 2k, you get this, the 2 to the k. For example, 2 to the k times 1 gives you that. 2 to the k times 2 to the negative 1, add the exponents, you get 2 to the k minus 1. Add these exponents and you get k minus 2. But we actually know what those numbers are, right? This turns out to be 1 plus a half plus a fourth, 7/4. Which is less than 2 to the k times 2, right? Because 7/4 is 1 3/4. And this is equal to 2 to the k plus 1. And that's what we were wanting to show. We needed to show that f of k plus 1, where did I say 1? Here, we needed to prove this, and we just did. F of k plus 1 is less than 2 to the k plus 1.